Bertrand, da Universidade Paris-Dauphine. Ele terminou o doutorado em 86, na Universidade Paris-Dauphine, e atualmente ele é professor associado dessa universidade e membro do CEREMADE. O CEREMADE é um centro de pesquisa em matemática aplicada. Por exemplo, um dos membros do CEREMADE recebeu a medalha Fields. E o interesse dele na pesquisa é sobre conjuntos ordenados, análise de agrupamento e estrutura de agrupamento que estende o modelo hierárquico. Então, ele está aqui por 2 semanas e hoje ele vai apresentar um seminário intitulado Multilevel Clustering Structures Defined as Interval Convexity with an Application to Machine Learning. So thank you very much, Patrice, to be with us, to spend your time with us, and so you can start. Thank you very much.
Thank you very much also. The talk I will present you is about multi-level clustering structures and their connection with interval, and there will be an application to machine learning. This is a joint work with Jean Diatta from the Université of La Réunion. So my talk is organized as follows. The first 2 items will be related to some very basic notion about index hierarchy and ultrametrics. This is just recalling. And the third items, the third following items are more new. Let us first recall the aim of cluster analysis. The aim of cluster analysis is to divide a ground set of objects into groups that are called clusters. And these objects must satisfy the following constraints. If they are in the same cluster, they should be closer than if 2 elements are in the same cluster. Then each of these elements should be closer than if they are compared with another element outside the cluster. So this is a very well-used machine learning tool, for example, in pattern recognition, in community, in phylogeny, and so on. I will just, from a general point of view, will just insist on the fact that there are 2 important choices that the data analyst must do before doing a cluster analysis. And these choices are the type of clustering structure which is determined and which clustering criterion. And indeed, these choices are very crucial for the result which is obtained. For example, we can decide to determine a partition or a hierarchy or pyramids or covering. And in each case, the organization of the clusters are very different between the clusters. And note also that the similarity or the dissimilarity which is considered on the data set is also a very important fact. Just have a look on the different clustering structure. Here we will mainly be concerned with hierarchical clustering structure, which is shown here. This means that we consider that 2 clusters are either disjoint or nested. For example, for the partition, any 2 clusters are disjoint, but also you have the constraints that the union of all the clusters is equal to the whole set S. Covering is different in the sense that we just need that there is no nesting between two clusters. So there is connection between, for example, the hierarchical clustering and the partition clustering structure. But I will not insist on this point. I just want to recall that when you are doing hierarchical clustering, you are also indexing the cluster by a map. Here I note the map F, such that this map is compatible with the system of clusters, in the sense that if A is including B, then f of A is strictly less than f of B. You have just to think that the meaning of f is the degree of heterogeneity of the cluster. So here, if two clusters are included in each other, then the smaller one has less heterogeneity than the largest one. Just to make the thing more concrete, I will, for this recalling of the hierarchical clustering structure, I will illustrate the notion on this basic data set, which include 6 objects in the Euclidean plane. And as you can see, there is the collection H is hierarchy, because two clusters are either disjoint or nested. I will not detail what we call the trivial clusters. The trivial clusters are the singletons of S and S itself. And so we have the following indexing. With the singletons, the level or the value of f on the singletons is 0, and we have this value for non-trivial clusters. So this index hierarchy can be represented by what we call a dendrogram, where the clusters are represented by horizontal segment. For example, W, X, Y, and Z are represented by the segment whose level is 2.24. 2.24 is the value of f on W, X, Y, and Z. And so you have a very easy way to visualize your clusters. In order to explain why this dendrogram indeed was obtained by applying what we call the HAC algorithm, the hierarchical agglomerative clustering algorithm, which is the well-known hierarchical clustering method. So I will explain how this dendrogram was obtained. So let us first recall what is the HAC algorithm. And for this, I need to introduce the notion of dissimilarity and leakage function. The dissimilarity is any mapping, which is defined on the Cartesian product of S onto R plus. It is just from a formal point of view, it's just a symmetric function, which is positive and whose values on the pair x for any x is equal to 0. And this means that the dissimilarity between x and x is 0. And So the aim is to measure the similarity or the dissimilarity more precisely between objects. A linkage function, here I notice D, is a generalization of a dissimilarity in the sense that it measures the dissimilarity not only on singletons, but also on any pair of subsets. So when, in general, we suppose that the subsets are disjoint because the algorithm HAC needs only to compare disjoint cluster. So, for example, here for the single linkage, we measure the dissimilarity between subset A and subset B just by computing the minimum dissimilarity between an object of X and an object X of A and an object Y of B. And there is a similar definition for the complete and the average linkage. The word linkage is more specific in the sense that it compares the centroid of the two clusters. So here is the HAC algorithm, which we need to define the linkage function, and the input data is a set S equipped with the dissimilarity delta. At the initialization, the hierarchy consists only of the n singleton of S, and the value of F is equal to 0 on each singleton. There is two main steps, which are the merging and the update. First, the merging step consists to merge subset A and B whenever these subsets are the closest pair, in the sense of D, among all pairs of clusters that have not been yet already merged. I mean that only clusters that have not already merged can be considered. That means that a cluster is merged only once, not twice. And then once this merging has been done, we compute the value of D between the new clusters and the other clusters in the already those we have not already merged, and we set that the level of the new clusters is the linkage function, the value of the linkage function between A and B. And we repeat steps 2 and 3 until the whole cluster S is formed. So let us come back here to the dendrogram. So you see that the first step was the merging of W and X, which are effectively the points which are the closest between each other among all the singletons. Once this is done, W and X cannot be merged once more, and you have to consider the cluster WX as a whole, and it is merged with singletons Y, but we could have also merged it with a singleton Z. Indeed, because the single linkage is the same value as the same value. But so there is an undetermined choice, but it's not in the final, because in the final step that I don't indicate here, the cluster 2 will be pruned, will be deleted, because it does not respect this action, because the level of cluster 2 is the same as the level of cluster 3. So in this case, cluster 2, which is included in cluster 3, will be deleted to preserve this constraint. So we have, and the final step, we have this this hierarchy, and we can associate with each index hierarchy a dissimilarity in a very simple way, which consists to define the induced dissimilarity from an index hierarchy as the value of the level, the smallest level of a cluster that contain X and Y. For example, here, the value of the induced dissimilarity, X and Y, is 2.24, and so on. So the value, the induced dissimilarity between W and X is 1.41. There is nice property between index hierarchies and ultrametrics. Indeed, let us recall that dissimilarity is called an ultrametric if it satisfies this strong metric inequality in which we have replaced the sign plus between U, X, and Z, and U, Z, and Y by the operator max. In this case, there is a very particular geometry of the object, in the sense that each triangle is isocel with the basis less than the two sides which are equal. And it can be proved that the induced dissimilarity from any index hierarchy is an ultrametric, which is called the cophonetic ultrametric induced by the index hierarchy. And there is a bijection between index hierarchies and the set of ultrametrics, which is based on the property, the second property here, double I. So there is another property of this ultrametric induced by an index hierarchy in the case where the index hierarchies is obtained by the single linkage. In the case where the hierarchy is single linkage hierarchy, these index hierarchies induce an ultrametric which is very special, in the sense first that this induced ultrametric is lower, its value are lower than the initial dissimilarity delta, which is simple to understand because we take, at each step, we take the minimum of the dissimilarity between the two clusters. And not only this fact, but also the fact that if an ultrametric is lower than the dissimilarity delta, then this other ultrametric is necessarily less than the ultrametric induced by the single linkage hierarchy. So we have, and it is the only one which has this property. So it is the maximum lower ultrametric for the dissimilarity delta, and it is called the subdominant ultrametric. So this subdominant ultrametric plays a specific role in the following of this talk. Let us first characterize this subdominant ultrametric in another way, which is pleasant for computing. We can compute the subdominant ultrametric very easily without constructing the single linkage ultrametric. In this way, let us consider X and Y, for example. Then the dissimilarity that we call delta star is the minimum value of a maximal jump along a path that joins X and Y. For example, in the green path, the value of the maximal jump is the jump between V and Y. For the black path, the minimal value, the maximum jump along this path is between W and 1. So you can see here, it's easy to see that the minimum, the lowest, the minimum maximal jump is indeed obtained on the black path, and this defines the dissimilarity delta star. And it turns out that the subdominant ultrametric can be computed in this way. So we have, I go back to multi-level clustering structure, and then I will be back to subdominant ultrametric again, but later. So let us recall that the hierarchical structure is characterized by the fact that two clusters are nested or disjoint. We can weaken this property by assuming that the intersection of three clusters is reduced to two of them. This is not so strong than the hierarchical property. And then we can define the terminology, usual terminology of hierarchy, which consists to assume that it contains also the trivial subset. In the case of weak hierarchy, we have also to assume that it is closed under non-empty intersection. So I will now make a link with the convexity, or more precisely abstract convexities, and we will then go back to the subdominant ultrametric. First, what we call by abstract convexity, it is just to say that the collection of subset is closed under intersection, and it contains S. The empty set here, we will not suppose that the empty set is contained, because in a multi-level clustering structure, which is closed under intersection, we always assume that the clusters are not empty. So I will focus on a special type of convexity, and I need to introduce the notion of interval function, which is a symmetric map defined from the Cartesian product of S into the collection of subset of S, which is symmetric in the following sense, and which contains the two born X and Y, the two elements X and Y. And we will say that the subset is convex with respect to an interval function I if the value of, if the subset X of the interval of X and Y is contained into C, X and Y belong to C. And so this condition is sufficient to ensure that the set of convex set form convexity. It is closed by non-empty intersection. And so, and this in this case, this convexity will be called the convexity induced by the interval function I, and it is called an interval convexity. I just want to mention that we are now considering different interval convexities, which are constructed or built from a map G, which is defined again from the Cartesian product of S into the whole collection of the whole collection of subset of S. And this map will satisfy some actions, but not all of these actions. But the first one is very close to the notion of interval function, because it just says that it contains the two elements x and y. The second, third, and fourth condition are technical, and I don't want to detail more specifically this action. I just want to mention that the fourth one implies the second and third one. W prime imply H and W. And these axioms are very general, and they allow, we will see that they allow to construct interval functions which are of interest. So let us first symmetrize the function J by considering the union or the intersection with J bar, which is defined as you can see. In this case, the symmetrized G by union or by intersection are interval function. And moreover, the symmetrized by intersection is necessarily included in the symmetrized function by union. And so that we have this inclusion when we compare the two convexities induced by union and by intersection. But the more interesting result is the following one, which make a connection between the multi-level clustering structures and the convexity. And it says that the collection is hierarchical if there exists a map J that satisfies C0 and axiom H such that C is equal to the convexity induced by the function, the symmetrized function of J obtained by union. And we have a similar characterization of weakly hierarchical multi-level clustering obtained by the symmetrized function of J obtained by intersection. And the fact here which enable to come back to our dissimilarities and subdominant and so on dissimilarity, subdominant ultrametric, is the fact that if we consider the map ball of delta, then the map ball of delta is defined as you can see. It is the ball of center X and radius, the dissimilarity between X and Y. Then this map ball satisfies axiom W prime, and W prime implies H and W. So we are sure that we can construct hierarchical and weak hierarchical multi-level clustering just by considering the map ball of delta. So what we are obtaining now is the following. We consider the symmetrized function obtained from the map ball of delta in two ways, that the way by G or by M. And we obtain a hierarchy if we consider the symmetrized function by union, which is indeed very well known and which is called the Aprendizado hierarchy of delta, in which each Aprendizado cluster is characterized by the intuitive notion of cluster that the dissimilarity inside for two elements inside the cluster are less than the dissimilarity of each element outside the cluster when you compare with the two elements inside the clusters. The second structure, which is a weak hierarchy obtained by considering the symmetrized function of the map ball with intersection, it is called the bundled and dress weak hierarchy. And it is also characterized by this inequality, which is relaxed when you compare with the first inequality related to the apresent clusters. And so we have this proposition, which is just the application of this inequality that you can see here. Conv of G and J is included in conv of M and G. So let us come back to the subdominant ultrametric. The subdominant ultrametric was defined as the smallest jump, the smallest maximal jump on any path from X to Y. So the idea is to consider all the dissimilarity obtained by considering only path of length at most L from X to Y. Then we obtain something which is a dissimilarity. We will vary the value of L, but so we will obtain many dissimilarities that are function of L. But it is clear that these dissimilarities are not ultrametric. There is no reason. But you can see that they are, it is easy to see that they are decreasing. For L equal to 1, you obtain the initial dissimilarity delta, because it's just the jump from X to Y, so it is equal to delta. And for L equal to n minus 1, you obtain the subdominant ultrametric, because this is the length to obtain all possible paths from X to Y without looping. So if you don't if you avoid here, we don't need to have looping. It does not add any information. So we limit the value of L to n minus 1. So we have this decreasing series of dissimilarity, and we look now about what. Well, first we look about some property of this series. This series is indeed easy to compute in a recursive way. Just see the first property I, and also it is stationary at some value of L. It becomes stationary. So we don't need to use the value of L equal to n minus 1. It often the case that the value of L is less than n minus 1 to obtain a stationary series of dissimilarity. So we notice this minimum value from which the dissimilarities are equals. We denote this minimum value as R of delta. And we simplify the notation in this way. And now we are looking about the apresent hierarchy of this dissimilarity delta L. First, we observe that the convexity of the symmetrized function of the dissimilarity, the symmetrized function of the map ball of the similarities delta n-1, which is the ultrametric subdominant, is necessarily the single link hierarchy. And also, it is not so clear to prove. We observe that the sequence of the convexity G subscript L1 and G convexity of G subscript L2 is increasing with the value of L. This is not easy to prove, indeed, and so we use the following notation. We denote by H and subscript L of delta the convexity of the interval function GL, and we observe that there is an increasing sequence of hierarchies, which correspond to the different value of L. For the dissimilarity, the increasing series is decreasing. The series of delta L is decreasing, and here the series of the hierarchy are increasing. From it starts at the à présent hierarchy of delta, and it ends at the single linkage hierarchy of delta, which is obtained not. There is a missing. No, it's okay. So observe that a cluster of the single linkage is there. Any cluster is there within one of these hierarchy. You have necessarily, if you take a cluster in the single linkage hierarchy, it necessarily belongs in one of these hierarchy. And the first, indeed, the first value of L, the first value of L for which the cluster C belongs to HL is called the chaining length. And it is clear that if we take the maximum value of all chaining lengths, we obtain a value L bar at which, from which all the hierarchies are equals. That means that the series of the hierarchies HL is stationary when you consider the value L equal to lambda bar. So we have this property, and it is easy to see that lambda bar is less or equal to R of delta. Let us see now how to apply this to have some application in machine learning. First, this was observed by different authors, but there is for value of L very small in general, we have a strong decreasing of the distortion between delta L and the subdominant ultrametric delta n-1, n-1. This is a very short time to obtain a value dissimilarity which is close to the subdominant ultrametric. And this is important for the cycle. The second point is that does it mean that we can simplify the dendrogram of the single linkage just by considering the value of HL of when the distortion between delta L and delta subscript n-1 is very small. Not necessarily, because there is no bijection between delta L and the dendrogram which represents the index hierarchy, HL. So we need to use the bijection that we have already seen between ultrametrics and the index hierarchy, which are represented by the dendrogram. And if we use this cophynetic ultrametrics, the distortion is not so easily obtained, because we have this distortion. It is always on the high-res data set. As you can see, the distortion is again very small, but not for value of 5, but more or less for the value of 10. This is due, again, because we have this property here, which is not here. We can have two distinct interval functions which induce the same convexity. And so here we have indeed you can see here that for example, here the value that you can see here, the value of rho L induce the same hierarchy as this one, as the one which is induced by delta L here, but the distortion is not the same. And so we have to use something which is coherent, and we have to use the bijection of Johnson-Benzekri. So what is the interest of this approach? First, we can simplify when the distortion is low. We can just use the aspersion of the dissimilarity delta L to approximate the hierarchy, the single linkage hierarchy. Here we have a part of the dataset, IRIS dataset. We have 84 elements, which are part of the 150 elements of the IRIS dataset. And if we subprime the all the clusters that are whose chaining length is greater than 10, we obtain the second figure B, which is more easily interpreted than the first figure A. Another point is about the interpretation. The clusters, aspersion clusters are generally of small size. And so we here justify, but it is not the case when the dissimilarity is approximatively ultrametric. This is explained by the following argument of continuity. So we have, if a structure exists, aspersion clusters are of size, interesting size, if the dissimilarity is nearly ultrametric. So here we can see that, for example, again, the distortion here is small, so we can suspect that the aspersion clusters are of size, interesting size. So this justifies to consider the convexity for L equal 4. And this also justifies that the quality of the aspersion cluster are interesting in the sense that we have a way to we have not what we call the chaining effect, which is a drawback of the single linkage, and because the length of the path is very small, so we have not the chaining effect on these aspersion clusters. So just I come back for the IRIS data set. You can see that the versicolor and virginica clusters, which are regrouped in the cluster B, are obtained with a value of L which is very small, 4, and Setosa is also obtained for a very small value of L, which justifies the existence of these two clusters and very coherent with knowledge about the dataset, the IRIS dataset. And we can select with this, we have indicated the size of the clusters in ordinary, and in abscess we have the value of size. We can select the value, the good clusters, by selecting those clusters which have a small ratio between the chaining length and their size. So I did not comment a long time this graphic, because it's a bit just to say that the decreasing in each graph, the decreasing, the difference between two points, successive points, this difference is decreasing. So this is a purely mathematical question. How to prove this? We have made a very numerous simulation, and we always observe this phenomenon, but it is not easy to prove. The difference, the value of difference is decreasing also. It's not only decreasing, it's the value of difference. So there is other research perspective. We see that the implication here is working well with the symmetries function G obtained by union, but it does not work with the symmetries function obtained by intersection. So why it works for this and not for the intersection, this is a question that can be explored. And another more practical direction would be to extend this approach to other hierarchical clustering schemes, such as the complete linkage or the average linkage, for example. Thank you for your attention.
Thank you very much for your presentation. Someone would like to make a comment, please.
Professor, thank you very much for your presentation. In the application on IRIS dataset, why the algorithm yield cluster with very small cluster? In your application to IRIS datasets, the algorithm found clusters 1, 2, 3 with small examples. Do you have some idea?
You mean, I guess that you mean why the aspersion clusters are generally small size. This is due to the fact that when you consider the characterization of aspersion clusters is here. As you can see, it is very, this condition is indeed very demanding. It's not easy for, in general, when you have clusters, you have clusters of a certain diameter. And it implies that the diameter of the cluster is necessarily less than the dissimilarity between a point which is exterior to the clusters and one point inside the cluster that realizes the diameter. So this is not very easy to obtain in practice.
Another question. So I have a question. So first of all, why it's important to simplify hierarchy? So I understood that, in fact, could you please show me the picture there? So, for example, you use this picture to select the point where to cut. Okay. And for example, in decision tree, which is a supervised method, you simplify also the tree in the sense that you avoid specialization, where with the class is very much specialized. But what are the meaning in the context of clustering when you simplify the hierarchy? What do you obtain?
It's just a global simplification. It's not local.
Okay.
It's just a way to say that we are. Just a way to say that we are representing an ultrametric, which is close to here. If we consider this curve, this can be seen as the computation of this distortion is obtained with an ultrametric. It is a representation of the cophonetic ultrametrics induced by the hierarchy. So it's just the representation of an ultrametric which is close to the single linkage ultrametric, so to the subdominant ultrametric. There is no interpretation in terms of clusters. Anyway, you have an interpretation in the sense that in this case, we are sure that the chaining length of each cluster is no more than 10. So it's a sort of advantage.